Okay, so for this video, I'm aware that exams are very close. Electromagnetism is going to be the last question in the exam, and we're just going to go over the last 2 years worth of questions. The first question asks, a simple circuit consists of a 9-volt battery and 3 resistors, where R1 is equal to 10 ohms, R2 is equal to 20 ohms, and R3 is equal to 30 ohms. And it also gives us that resistors R2 and R3 are in parallel, and this combination is in series with R1. So the question is asking for three things: to draw a schematic diagram of the circuit, to find the total resistance of the circuit, and determine the current through R1. So the wording of the question was very specific. It mentioned that R2 and R3 are parallel, and this combination is in series with R1. So we know that we've got a parallel component and a series component. So moving on to drawing this out, we have our power supply. We have two resistors in parallel with each other, which is then in series with a third resistor. The next thing that we might want to worry about doing is labeling our diagram so that we can come back and use it to help solve problems later on. But just as a rule of thumb, you do always want to be labeling your diagrams anyways. So the same as we've already done for previous questions, we're going to start off by following the path of a positive charge carrier, and that just means we're following the circuit from the positive side to the negative side. And the first thing we come across is a parallel set of resistors, but we already know which formula to use for that. So we take 1 over R23 to be equal to 1 over R2 plus 1 over R3, and so that becomes 1 over 20 plus 1 over 30, which is 3 over 60 plus 2 over 60, which is 5 over 60, which is equal to 1 over 12. So we know that the value for 1 over R23, or the total resistance, is 1 over 12. So if we take 1 divided by 1 over 12, the ones will cancel. And so R23 is equal to 12 ohms. And so what we've done effectively is we've taken the combined resistance from both resistors, and we can now represent that as a single resistor that's in series with resistor number 1. And so then to find the total resistance throughout the circuit, all we need to do is add up the different resistors that are in series. And so it then becomes 12 ohms plus 10 ohms equals 22 ohms. And so then the last part of this question wants to ask what the current through resistor 1 is. And for this is quite simple. We'll start off with Ohm's law: V is equal to I or, and I is equal to V over or when rearranged. We write down our variables, so we've got 9 volts as our potential difference. The resistance in total is 22 ohms, as we've just calculated, and so our current is 9 divided by 22, which with a little bit of help from the calculator is equal to 0.409 amps. And in this case, we can, if we want to, round that up to 0.41 amps. And with that, we have the answer to our question, but I want to take a moment to take a look at the system and see what's going on here. So we have a potential difference of 9 volts driving a current flow of 0.41 amps, leaving the positive terminal at a rate of 0.41 amps. That current will then split at the junction and recombine after the junction. And in the meantime, there will be a voltage drop as the charge carriers pass through the resistors. And because the two values of resistance between R2 and R3 are different, then the ratio at which the current splits at the junction is different for each branch. So we know that there is a total of 0.41 amps traveling through this circuit. But we also know that that current will split as it goes through both resistors. So what if the question wants to know what the specific current through each resistor is? So this question definitely levels up the difficulty a little bit, but the way I want to go about solving it first is I want to find the voltage drop on the R1 resistor, in order so that we would know what the voltage going through our R2 and our R3 resistors would be. Again, the voltage drop can be calculated using Ohm's law, But the reason why it's important here is if we know what the voltage drop across the resistor in series with the parallel portion of the circuit, then we'll know how much voltage is going through the two branches in total of the parallel circuit. And from that, we'll be able to find out how much current is being supplied to each of the two resistors. So that's our first step. So we know the resistance of R1 as 10 ohms. And we also know that it's being supplied with a current of 0.41 amps. And that allows us to calculate a 4.1 volt drop across the R1 resistor. So I think it might help if I draw this out again to help visualize it a bit better. But if we take the parallel branches of our circuit, move them down here a little bit, we'll be able to see a little bit better that we have a 9 volt potential difference as our power supply. We've lost 4.1 volts of that to the resistor R1, which means that we have a remaining potential difference being supplied to the parallel branches here of 4.9 volts. So we can now label our two resistors, and with the knowledge of what the expected voltage to pass through the two branches will be as 4.9 volts, we now have a voltage, we have independent values for resistance. We can just apply Ohm's law again, and that will give us a current value for the current flow through each resistor. And it is just a matter of reapplying Ohm's law once again. So we can just plug our values back into the calculator, and that's 4.9 volts divided by 20 ohms is equal to 0.245 amps, and 4.9 volts divided by 30 ohms is equal to 0.16333 reoccurring, which we can just round back down to 0.163. So with that in mind, we now have a branched current of 0.245 amps and 0.163 amps splitting across each resistor in this parallel segment, and then they will recombine back into the series component later on. And the way that we check this is just by adding up those two amperages together, and if they produce the same current that went into the system as what's coming out, then you've got your correct answer. So because Ohm's law itself isn't a technically difficult formula to use, it's just manipulation of fractions, exam questions will try and provoke out of you this sort of larger understanding of how voltage and current will relate to each other in more complicated systems. So this is the type of question that will really try and provoke this level of understanding in your problem solving abilities. So moving on to the next question, a 1.5 volt cell is connected to a light bulb that draws 0.5 amps. The bulb is lit for 5 minutes, and the question wants to know how much charge flows through the circuit and how much energy does the battery supply. So this question is kind of interesting because it is essentially a test on how well you know your definitions for current and energy. So we know that I is the flow of charge, and the units for that are given in coulombs per second. So if we want to know how much charge is supplied throughout the entire duration, we would just take coulombs per second and we would multiply that by time. So it's the current multiplied by the time in seconds. So when we do that, the seconds will cancel and we'll just be left with coulomb, our unit of charge, and we can then go about solving this problem. It's 0.5 amps times 5 minutes. 5 minutes is equal to 300 seconds. And so we get an answer of 0.5 amps times 300 seconds is 150 coulombs. So that's a nice question there. Then moving on to how much energy does the battery supply, when we can go back to our definition of energy as the capacity to do work, and we know that the unit for energy is the joule. So let's start off by writing down our definitions. V, our voltage, is the potential difference, and our I is the flow of current. So we've already calculated the amount of charge that will flow through the circuit in 5 minutes, which is the amount of charge exchanged or transferred by the electrons over the course of 5 minutes, and that's 150 coulombs. And then, knowing our formula for energy, we can just multiply the charge that's delivered by the potential difference, or E is equal to V times C as given in the log tables. And that then becomes 150 coulombs multiplied by 1.5 volts, which is 225 joules. And so again, really nice question. These are the types of questions you love to see come up, because really all it is asking, do you understand what charge is, and do you understand what energy is in the context of what we're talking about here? So moving on, we now have a question relating to Tesla's idea of magnetic flux. And the question is asking, an electron moves through a 0.15 Tesla magnetic field at 2 by 10 to the 5 meters per second. What is the maximum force it will experience, and what happens if the electron moves parallel to the field? So again, nice enough question. We don't have to spend too much time thinking about how we're supposed to go about solving this. All we need to do is go down to our log tables, find the force on the charge formula, which is F is equal to QVB sine of theta. And from there we can go about inputting our different variables. So we know our Q is the electron charge, because we're talking about an electron here, which has a standard charge of 1.602 by 10 to the minus 19. Our V in this case is velocity, not voltage, which the question gives us as 2 by 10 to the 5 meters per second. Our value for B, which is the magnetic field, is equal to 0.15 Tesla. And then the last thing we need to find is our value for theta. And so even without understanding how the system works, we know that if we are multiplying by a scalar of sine of theta, then that's just going to affect the magnitude somewhere between a value of 0 and 1. Sine of 90 is equal to 1, and sine of 0 is equal to 0. So the only possible answers will be somewhere between 0 and 1. Then we know the magnetic field will be strongest when theta is equal to 90 degrees. And so then when we go back to our definitions of how the magnetic field works, we know that the magnetic field will only act on a particle that is moving perpendicular to the field. So in order for the field to be its strongest, theta will have to be 90 degrees. So we can solidify our value for theta as 90, and then it's just a matter of inputting all of our variables into the function and then solving using our calculator. So we have F is equal to 1.602 by 10 to the minus 19 multiplied by 2 times 10 to the 5 meters per second by 0.15 Tesla multiplied by the sine of 90 degrees, which is equal to 1. So when we solve for all of that in our calculator, we get an answer of 4.806 by 10 to the minus 15 newtons, which is the amount of force enacted onto the electron moving perpendicularly through the field. And so the next part of the question asks what happens if the electron moves parallel to the field. And again, without any technical insight into how the system works, if we're moving parallel to the field, then we are moving at an angle of incidence of 0 degrees. And so sine of 0, it goes to 0. And so anything multiplied by 0 is equal to 0. And therefore we will have a net force of 0 newtons acting on the particle if it is moving parallel to the field. So the next question asks, a straight wire carries a 3 amp current in the positive x direction and is placed in a uniform 0.2 Tesla magnetic field pointing in the positive z direction. What is the direction of the force on the wire? And calculate the force per meter on the wire. So the setup for this question is quite simple, but if you're struggling with how to even start a question like this in an exam, you can always go to the back of the book and check the log tables. In this case, we are given a force on a wire equation where F is equal to the current times the length times the strength of the field multiplied by the sine of theta, or F is equal to ILB sine theta. So we can start this question off by just drawing out the diagram of the system. We know that the field is moving in the positive z direction, so we can just draw some field lines going in the direction of the positive z. And the current is moving in the positive x, so I can indicate that with just a little red arrow here going in the positive x. So our formula is given to us as F is equal to ILB sine theta. We know what our current is. It's given in the question. We know what our field is, our B, and we also know what our theta is. But we're not given a value for length. And in this case, because we are asked to find our answer in terms of force per meter, we can just assume that the length of the wire is 1 meter, and so that way the force acting on the whole meter, regardless of what the force is, will be in terms of per meter. So we can go ahead and start filling that back into our formula, and so it's 3 amps multiplied by 1 meter multiplied by 0.2 Tesla multiplied by the sine of 90 degrees, which goes to 1. And so our value for F is 3 by 1 by 0.2, which is 0.6 newtons. And because we assumed that the length of the wire was 1 meter, then our answer will be in newtons per meter, which is the format the question asks for. And now we know what the strength of the force is, we know the direction of the current, we know the direction of the field. We can use Fleming's right-hand rule in order to work out the direction of the force. And in this case, it's in the positive y direction. So with that, we're ready to move on to another question, and this one is a question on capacitance. So it gives us a circuit with one power supply and 3 capacitors in series with each other, in parallel with each other, where our first capacitor is equal to 2.6 microfarads. Our second one, C2, is equal to 5.5 microfarads, and C3 is equal to 3.3 microfarads. And the question asks, find the equivalent capacitance between points A and B for the 3 capacitors. So we should remember that our equivalent capacitance for capacitors in parallel is just given by adding them together. So all we have to do is add our C1, our C2, and our C3, which is equal to 2.6 microfarads plus 5.5 microfarads plus 3.3 microfarads, which is equal to 11.4 microfarads. So the next part of the question asks, what is the charge on the 5.5 microfarad capacitor if a 44 volt potential difference is applied to the terminals A and B for a long time? So in my opinion, this question is sort of designed to throw you off a little bit. Typically in physics, when time is mentioned at all, it is typically an important factor to consider when you're solving a problem. However, in this case, it doesn't give you a value for time, and time isn't really needed at all. And instead, what we're doing is relying on our definition of capacitance, which is given to us in the log tables as Q is equal to CV, where Q is the charge stored, our V is our potential difference, and C is the capacitance of the capacitor. And again, going back to our definition of capacitance, it is a measure of how much electric charge a system can store per unit voltage. So if we multiply that by our unit voltage, we will then get the value of electric charge. And we can see if we just write out our units here, our units for Q are the coulombs, our units for C are the farads, and V is volts. So if 1 farad is equal to 1 coulomb per volt, then C is equal to C over V times V. The V's cancel, and so C is equal to C. So we know that we should expect an answer in coulombs. So 5.5 microfarads multiplied by 44 volts is equal to 5.5 times 10 to the minus 6 by 44, which is equal to 2.42 by 10 to the minus 4 coulombs. And so there we have our answers to part 1 and part 2, and we're ready to move on to the next question. Now this one is definitely a more difficult one. Again, we're not going to be working with any crazy maths here, but the question is really looking to see how well you understand how current and voltage relate to each other by giving us a circuit with 3 potential differences, a total of 4 resistors, and by giving us the current at certain points. And so what it wants us to do is it wants us to recognize the patterns in the fixed relationships between current, voltage, and resistance. So let's go over the question here. It says, consider the following circuit. Find the unknown EMF epsilon 1 in the circuit. Assume R1 is equal to 4.6 ohms, R2 is 4.4 ohms, and R3 is 1.1 ohms, and epsilon 2 is equal to 2 volts. So the first thing we can do here is we can start labeling our resistors. We have given values for R1, 2, and 3. And we're also given a value for epsilon 2 as 2 volts. And so the next thing I want to do is I just want to label the positive and negative electrodes at each end and follow the path of current. And it was at this point I realized that we have 2 power supplies or sources of potential difference that are pointing in opposite directions. And so we're given at the bottom a potential difference of 1 volt, but at the top for epsilon 1, we know that its current is going to be pointing in the direction that opposes the direction of our 1 volt supply at the bottom. And this is a bit of a curveball, but we are also given in the question that there is a 195 milliamp current pointing directly up along the left side of the circuit. So that means that the voltage we're given at the bottom of 1 volt has to be greater than the voltage of epsilon 1. And so that 195 milliamps given to us in the question is a big clue as to figuring out what the difference in voltage between epsilon 1 and the 1 volt. And so the question has given us a current, a voltage, and a value for resistance as we follow that 1 volt potential difference across the R1 resistor. So one of them can't be correct. And in this case, it's because the epsilon 1 potential difference supply is pointing in opposite directions. So we know that some of that voltage is going to cancel out. And so if we apply the given current and the given resistance, then we'll be able to find what the actual voltage drop along that resistor will be. And so it's really just a matter of applying Ohm's law to calculate the voltage drop. And so we have V is equal to I, or I is equal to 195 milliamps, or is equal to 4.6 ohms. So it is 195 by 10 to the minus 3 amps multiplied by 4.6 ohms is equal to 0.897 volts. And so if we go back to the idea of where the potential difference comes from in a battery, we have electrons that are accumulating at a negative electrode, and the difference in potential between that negative electrode and the positive electrode are pushing those electrons down the wire and around the circuit. And so in this case, the way we've drawn it, we have the positive 5 volt face touching the positive 4 volt face. And so the electrons are going to want to move to the left. And because we use the typical convention of following a positive charge carrier, which means that our current will be flowing to the right. And so we'll have a net flow in the right direction as the electrons move to the left. So going back to the question, we know that there is a 0.897 volt potential drop across R1. And because the question gave us a current and direction the current is flowing in, we are able to tell that there is a 0.897 voltage drop across the resistor. The net voltage will be equal to 1 minus the 0.897, and that will give us our value for epsilon 1. And in this case, that's equal to 0.103 volts. And in this case, we didn't even have to look at the right side of the problem. However, if we wanted to check our answer, or if you want to do it as part of your own practice, I would recommend checking the answer by solving it from the right side, because it gives you enough information to do it in that direction as well. So we can move on to our next question now, which asks, a magnet produces a 0.47 Tesla field between its poles directed to the east. A dust particle with charge Q is equal to minus 5.1 by 10 to the minus 18 coulombs is moving straight down at 0.3 centimeters per second. What is the magnitude and direction of the magnetic force on the dust particle? So we can start off by drawing out a little plot here to see what's going on. We have a 0.47 Tesla field pointing to the right, and we have our particle that has a charge of minus 0.51 by 10 to the minus 18 coulombs that is moving downwards at a speed of 0.3 centimeters per second. We can go back to our log table and find the force on a particle equation, or I should say force on a charge, which is F is equal to QVB sine theta. And again, we know our Q, it's given to us in the question, our V, and again, in this case, it is a velocity, not a voltage, and it's 0.3 centimeters per second. Our B, 0.47 Tesla, and our theta. The theta is the only one we have to figure out, but we know because the field is pointing directly to the right and the momentum or the velocity of the particle is pointing directly downwards, theta will be 90 degrees, which maximizes the effect of the field on the particle. Whereas if we remember, if theta was equal to 0 or 180 degrees, then sine of 0 or 180 is equal to 0, and anything by 0 is 0. So we have F is equal to minus 5.1 by 10 to the minus 18 multiplied by 0.003 meters per second multiplied by 0.47 Tesla, and multiplied by sine of 90 degrees, which is equal to 1. And that gives us the answer of minus 7.191 by 10 to the minus 21. That minus sign for the 7.191 is because we didn't take the absolute value of the charge. In some cases you can. It just, again, requires that you are a bit more considerate as to the direction that these forces will be acting on. In the sense that if it is a positive charge, it will be repelled by the field, and if it is a negative charge, it will be attracted by the field. And again, that is assuming that we are moving perpendicular to the direction of the field, whereas if we were moving parallel, then nothing would happen regardless of the sign of the charge. And once again, we can use our right-hand rule to determine that if the particle is moving downwards and the field is pointing to the right, then we can determine that the direction of the force acting on the charge will be pointing in the positive z direction. And so with both parts of the question answered, we can now move on to the next question. And in the test I got this from, the question does provide a diagram. However, I'm just going to start off without a diagram and we can draw our own in. And so it asks a square metal loop of side 4 centimeters and resistance 5 ohms moves to the right, positive x direction, into, through, and out of a 6 centimeter wide region of uniform magnetic field perpendicular to the plane of the loop. The magnetic field in the region is 0.25 Tesla. At t is equal to 0, the loop begins to enter the region of magnetic field, and the loop moves through at a constant 1 centimeter per second. And so the question is asking to draw a graph of the external force applied to the loop as a function of time. So we can start off by drawing out our square loop of side 4 centimeters. We know that it's moving to the right, so we can make that our positive x direction. And it's moving into a uniform magnetic field. And in the diagram the question provided, it indicates that by putting down a load of x's. Typically in these types of questions, x's indicate that the field is moving away from you, whereas if the field was moving out of the page toward the reader, so towards you, then it would be notated by putting little circles with a dot in the middle. And so in this case, the question isn't necessarily requiring you to need that to solve, but it's interesting and handy to know. So we can, from this point on, assume that the magnetic field is pointing into the page. So let's talk about what happens when the loop enters the region of the field. So we know that the metal wire has loosely bound electrons, so as they move into the field, the flux will change. It will very instantly be quite high. This will induce a current as it's moving through the field, and that induced current will induce a magnetic force. that opposes the direction of the movement. And so in order to keep this loop moving through the field at a constant speed, an external force must be applied in order to push the loop, and that external force must equal the strength of the magnetic force. However, because the region of the field is larger than the area or the width of the loop, when the loop is fully inside the field, there will be no change in the flux, and so there will be no change in the flux, which means it won't be inducing a current, which means that there won't be an induced magnetic force, which means that the amount of force needed to push it through the field will decrease. And so with that, we're ready to go back to our diagram. And the way it's presented to us here, we know that the loop is outside of the field at t is equal to 0. And it will progress to the right at a rate of 1 centimeter per second. So if the region is 6 centimeters wide, it should take 4 seconds for the loop to fully move into it, and a further 6 seconds in order for the loop to move through it, and a further 4 seconds in order for the loop to be completely outside of the region. And so in total, that brings us to 4 plus 6 plus 4, which is 14 centimeters at a rate of 1 centimeter per second. That gives us 14 seconds of movement. And so if we want to plot this as a function of time, our time axis is at the bottom and our force is at the top, or on the y-axis. And what we will do is we would start this function initially experiencing the maximum force, and as the formula that gives us the force on a wire due to the field involves a sine wave, we would draw a sine wave decreasing from the maximum force down to 0 with a 2-second break, and then it would start climbing again as more of the loop is leaving the field, inducing more of a current and more of a force, and it would finish backwards started. And so with that, we've covered all of the electromagnetism questions from the last 2 years worth of exam papers. If there's any questions on anything I've gone over, drop me an email. And other than that, I wish you the best of luck in your exams. Have a good one.